Shading with set operations. I want to show you how we can use shading to find the solution to set operations. And on this page I have 4 examples of 2 set operations with 2 sets, and went ahead and drew out the 4 Venn diagrams. And these numbers that are in the sets 1, 2, 3, 4, that's just going to help us at the end. If there's, so we would say that A contains the elements 1 and 2, B contains the elements 2 and 3, and then in the universal set that's not in A or B is 4, and then that'll just help us to be specific at the end of what parts of the Venn diagram are included in the result. So I just put a number in each of the 4 regions of each one of these Venn diagrams. Let's take a look at this first one. A complement, union, B complement. Union just means bring it all together. Union says anything that's a part of either A complement or B complement, one or the other or both. And so when you're trying to shade for a union, you can just go ahead and shade away, and then anything that's shaded, whether it's shaded as a part of A complement or shaded as a part of B complement, or if it got shaded twice, that's not a problem. This is just going to bring all that together. So A complement, that's everything outside of A. So working our way around this circle that represents the set A. So that's everything outside of A, and if you want, you can remind yourself that that's the symbol, the shading pattern that we use for A complement. And then B complement, everything outside of B. So that would be, no pun intended there, that would be out here, everything around B, and this is going to cross over into A because 1 is outside of B, right? And so you'll see here that if we take the union of all that, what is included in those parts that are shaded once or twice, it's going to be 1, 3, and 4. Well, what do you notice is not there? It's 2. 2 would be the intersection. Another way to say this is everything except the intersection. Well, if you remember DeMorgans Law, if we took A intersect, whoa, there's not a C here, A intersect B, and we took the complement of that, DeMorgans Law tells us that is equivalent to A complement union B complement. So these two are the same, and we can see this by shading A complement union B complement. That's everything except the intersection. So it's the complement of the intersection. That's A complement union B complement. On the second example, this is A complement intersect B. So the result has to satisfy both of these to be in the intersection. Has to be outside of A and in B. So let's shade this one way, let's shade B the other. So A complement, everything outside of A, and then the result is going to be those regions of this Venn diagram that are shaded with both patterns. So this is everything outside of A. Okay. So in that case, it's going to be 3 and 4, but has to also be in B. And so what's the only region in this Venn diagram that's shaded both ways, both patterns? You can see that's just 3, the region with 3 inside. Well, hopefully that looks familiar. This shape right here, if we started with B, which is 2 and 3, and then we removed A, so take the difference, a relative complement of A in B, we took B minus A, that would leave just 3, because if A is removed A, only 3 remains. So B minus A is the same as A complement intersect B. That's, you know, that's a definition. That's one of the ways that we could write difference in terms of intersection. Okay. And let's try this another way. You may have a clue on how this works. At any time, if you want to pause the video and try these on your own, you could pause it right now and give this a go. Okay. This is going to be A complement. Figure out what that is, and then if we removed B, from A complement, what would remain of A complement? Give it a go. Pause and start it up here after you've given this a try. Okay? All right, so hopefully you've given this a try. A complement is going to be everything outside of A okay, so that includes all of that, everything outside of A. But if we remove B from this, if we remove B, because right now as it is, A complement includes 3 and 4. But if we remove B, that's going to take 2 and 3. 3 and 4 are part of A complement. If B is removed, then what remains is only 4. Okay? 3 and 4 are an A complement, but if B is taken out of the picture, what remains outside of A? Just the 4. Now, let's go back a step here. When we had A complement minus B, okay, A complement minus B, when you subtract A, we could write that as B intersect A complement. Intersection is commutative. Okay, so B minus A is equivalent to B intersect A complement. Minus A is equivalent to intersect A complement. Minus B is equivalent to intersect B complement. Okay? Now, if we think about DeMorgans Law, everything is outside of A and everything outside of B, outside of A, outside of B. 4 is the only thing that's outside of A and outside of B. But DeMorgans Law tells us that A complement intersect B complement is the same as A union B complement. Anything that's not in the union. The union would be 1, 2, and 3, right? So 1, 2, and 3. What's not in the union? 4. Okay. So DeMorgans Law actually pops up quite a bit when you're working with shading and the difference and the complement. Right? One last example when we're working with two sets. This is the symmetric difference. One way to think of the symmetric difference is the union of A with B complement. The union of A with B complement, but not the intersection. The union, but not the intersection. So A is going to be this, A includes 1 and 2. B complement, we can go ahead and do that in one step. Let's shade B complement, so everything outside of B. Now, since we're shading this two different ways, the regions of this Venn diagram that are in the intersection are going to have both patterns of shading. And the symmetric difference looks for any region of the Venn diagram that's a part of the union but not the intersection. So anything that's shaded once but not twice. Okay? All of this out here is shaded once. This region containing 1 is shaded twice. This intersection here is shaded once. So when it talks about, when the symmetric difference is looking for the union of these two, but not the intersection, that's going to be anything that's shaded once. So that's going to be 2 and 4. Why not 1? Why not this region here? Because it's part of the intersection. It was shaded as a part of A and also a part of B complement. So not that. Okay? No, not the intersection. So there you go. Those are some examples of how we use shading to figure out the results of these set operations with two sets.